My name is Sakina Walji and I'm the director of SILT. I want to welcome everybody here in person and also the people who have joined online. We've had a wonderful sign up for this series. We've had over 125 sign-ups across the two lectures. And so a very warm welcome to you wherever you are. If it's your first SILT event, you are very welcome. I'm going to introduce John very, very briefly. My intro doesn't cover his extensive CV and accolades, but Google is your friend for that. Okay, so Associate Professor John Shock is an Associate Professor in the Department of Maths and Applied Maths at UCT, and his research interests cover machine learning, theoretical physics, and neuroscience. He's also an innovative and charismatic teacher and a former winner of UCT's Distinguished Teacher Award. And I'm going to stop there and hand over to you, John.
Great.
Thank you very much for the first part one of the AI lectures. Thank you.
Pleasure. Okay. I should stop there. So thank you very much, everybody, for coming along, for taking out your lunch break to be here. And thank you very much for the invitation. I think it's really nice that we're talking more about these topics, and hopefully I'm going to give you a little bit of insight into how we got to where we are today in terms of some of the AI we're seeing. Can I do this?
You'll be able to go left and right.
Oh, there we go. Okay. So,
sorry. My effort misbehaving now.
no worries.
I could kill it.
We're all good. Okay. No worries. So yeah, we find ourselves at a kind of unusual time in human history where up until now we've had some sort of projection as to where we're likely to be technologically in the short to medium term. You know, we have some idea that a year down the line the world is not going to look very different from how it is today, possibly politically, possibly economically, but in terms of technology, you know, we've had a fairly good understanding of the trajectory. And that's just not true anymore in terms of technology. We're finding that, in particular with OpenAI and other organizations, ChatGPT and the like, have really changed the game. And it's not just about language generation, it goes so much further than that. And all of this comes about because of a number of different factors that have come together, one in terms of the computational power that we now have, and two in terms of the algorithms that have been developed. And what I'm going to be talking about here is a fairly sort of narrow view of AI. And if you speak to other people working in artificial intelligence, they'll tell you a very different story. And it's not that their story is wrong, it's just quite different perspectives on the same thing. I'm going to be talking about this more from the perspective of so-called deep learning or neural networks. There are people at UCT, people like Tommy Mayer in computer science, who work at the cutting edge of quite different aspects of artificial intelligence, aspects of formal logic, aspects of reasoning, knowledge representations, these sorts of things, which I'm not going to go into in any detail, but it's not to say that these aren't important areas. But I think that in terms of the revolution that we're seeing at the moment, deep learning, neural networks, it's really important to understand these and the history of them to understand where we are now. Okay, so I'm an associate professor in the Department of Maths and Applied Maths. I don't come from a computer science background. I'm not sure why you should trust me, but here you are. So I started in physics, and I've been sort of working in theoretical physics and then more and more in machine learning over the last few years. And I'm very keen on the sort of interdisciplinary nature of science, that there's a huge amount to be gained from people working across different fields. And it's not to say, and one has to be very careful of this, it's not to say that a physicist comes along and solves all the problems in other areas, which you may find physicists are want to do. But I do think that it's important to take skills and ideas from one area and see how they can be bridged to other areas. And so I'm coming in, as I say, with a very particular perspective on this, but hopefully most of it is relatively neutral. Okay, so I want to talk about the history of AI. And there's a question of, you know, where should one begin with this? Do we talk about Ada Lovelace, who was really the first computer programmer, first software developer, who actually essentially wrote about the ideas of computer programs before there were computers in the way that we think about them today. So Babbage's difference engine was created as this idea, but actually wasn't instantiated at the time. But the idea of a programming language came about through Ada Lovelace. We could talk about the Mechanical Turk, so this amazing chess-playing robot from the 1770s, I think it was built. Does anybody know about the Mechanical Turk? So this was an amazing chess automaton that could play chess automatically against some of the best players in the world, and it toured around Europe for a very, very long time, beating everybody. In fact, I think it was around 80 years. It was traveling around playing against people, and this is pretty amazing, seeing as it was only with Deep Blue that a chess engine from IBM was able to beat Garry Kasparov, on the order of 20 years ago now, and yet in 1770 they already had this. It was a bit of a it wasn't quite what they said it was, though, because in fact there's enough space in there to put somebody who's quite good at chess, and that's actually how it worked. That there was somebody in there moving the pieces about from below. So okay, it's not quite the chess automaton it was promised to be. We could also start with Alan Turing, really sort of the grandfather of computer science. Did a lot of amazing work in information theory, and really our understanding of computers and what computer science means, thinking about algorithms, and indeed thinking about artificial intelligence. But we're not going to start with any of those. We're actually going to start somewhere not related to computers at all and go to 1890 in Spain, and Santiago Ramón y Cajal, who was a neuroscientist, who drew these amazing pictures of neurons in the brain. And he noted that there were lots of different structures of neurons in the brain, but they all had sort of some similar physiology in terms of the basic structure, even though they actually look quite different. And this really revolutionized our understanding of what was going on in the brain. We didn't understand it fully from the electrochemical perspective, but it gave us a picture of the fact that the brain was made up of this network of neurons, and somehow signals traveled through these neurons and gave rise to the experience that we have here. So you can take these ideas from Ramón y Cajal, and you can say, okay, what are the key ingredients here? What's actually happening in a neuron? And we have these wonderful experiments now, so-called patch clamp experiments, where you can take a neuron and you can put electrodes into the neuron and ask what's happening. Okay, what's happening in terms of a signal traveling down the neuron? And the basic idea is that you have a neuron here, which is this whole thing here, which is linking up to a second neuron, and they link together by synapses. And here we have an axon and a nucleus and the dendrites, and signals essentially come in from a prior neuron into the dendrites of a new one. They send through some little signal, and that signal is built up, integrated, and if there's enough incoming signal, this one sends a signal down the axon and triggers further signals in the neurons that it's connected to. So what we have in our brain is this electrochemical process. So essentially there's an electrical signal that passes down here, but in fact that's really happening by chemicals transferring through the membrane of the neuron. So we have in our brains these very, very complex structures of billions and billions of these electrochemical processing units, and that's going to be very important in a moment. And all that's happening is that essentially signals are traveling down them, and either they are or they are not passed on. Okay, and this is quite important. So essentially, a neuron passes a signal in a sort of binary way. It either passes a signal or it doesn't. Okay, the connections between them, the synapses, might have some weight. So it might tell you about the importance of a pass signal coming into the next neuron. But the signals themselves are, in a sense, binary. I mean, there's a little hand waving there, but in a sense, they're binary. A neuron fires or it doesn't. Okay, we change tack again and go to the early 20th century, where Whitehead and Russell put together this book, the Principia Mathematica. And the idea of this was to try to lay down the formal foundations of mathematics, formal logic, from an axiomatic system, from a complete base. And the question was, can we build up all of the knowledge of maths that we have from very, very simple ingredients, from so-called formal logic? Okay? And this, I think, is on something like page 397. I don't remember. The whole thing is a couple of thousand pages long. This is from page 397. And finally, we get to, from this proposition, it will follow when arithmetical addition has been defined that 1 + 1 = 2. So it took around 400 pages to prove that 1 + 1 = 2, which really tells you quite how sort of fundamental this is. This isn't saying, okay, we already know about addition. We know that 1 + 1 = 2. This is, how do we prove that? Okay? Which seems in some sense very easy, and then you think about it a bit more and you go, actually, where do we start from? And so Russell and Whitehead tried to make this sort of formalization of mathematics complete. Actually, it turned out later from Kurt Gödel that this was impossible. Okay? I'm not going to go into the details of this, but Gödel's incompleteness theorem told us that actually, although you could do a great deal with this, there were always going to be questions that you could ask, mathematical questions that you could ask, which were unprovable. You couldn't prove whether they were true or false, even though it might be that they do have some truth or falsehood. You couldn't prove that whether they are true or false. Okay, so this Principia Mathematica, a very, very complex book. So now we come to Walter Pitts, 1935 in Detroit, and Walter Pitts is running away from a group of hooligans down the street. He ducks into a library. The hooligans race past, don't find him, and he finds a corner and hides out there in the library. And sitting around, he comes across the book, the Principia Mathematica, and he starts reading it. In fact, he starts reading it and he reads it for 3 days. He sits there, he hides out in the library, they close the doors, they don't notice he's there. He reads through it, he thinks this is brilliant. This is the most kind of, I don't know about entertaining, but sort of enthralling thing he's ever read. Even though we can see from here, you know, it's pretty complex stuff. He's reading through this thing and saying, there's some deep truth here. This is really important stuff. So Walter Pitts then writes to Bertrand Russell and says, I read your book, thought it was great. I'd like to talk about these ideas. And Bertrand Russell writes back almost immediately and says, this is great, you know, with what he'd written to him, it's clear that you have a deep understanding of this. And he invites him to come to the UK to come and do research. There's a problem at this point, and that's that Walter Pitts at this time is 12 years old. He has to turn down the offer. But about 3 years later, Bertrand Russell is actually in the US, I think at the University of Illinois, and Pitts runs away from home, goes to the lecture, speaks with Bertrand Russell, still sort of enthralled by these ideas 3 years later. He actually never returns home. And in the lecture, he meets up with Jerome Letvin, who becomes a lifelong friend, although actually Pitts didn't live all that long. He died from liver cirrhosis, had a short and not terribly happy life. But Letvin becomes a very close friend. And the two are really different sorts of characters. So Pitts is this incredibly logical character who is deeply in love with mathematics and the ideas of formal logic. And Letvin is interested in poetry and biology. And, the two seem to be fairly different. At this time, Pitts goes along to a class of another logician, Rudolf Carnap, and a sort of similar thing happens. He goes along to Carnap's office and says, hey, I read your book, I found some errors in it. And actually, it does turn out that there were some errors in the book. Carnap is an extremely important logician at the time. And Pitts then leaves in a sort of goodwill hunting style thing. Carnap believes, this must be some, grade A student. And it turns out he's not at all, and it takes him months to find him. He eventually finds him, gives him a sort of menial job. And the two start discussing and working together. Jerome Letvin, by this time, is now doing a medical degree and is working with Warren McCulloch, who's his supervisor. And Letvin introduces McCulloch to Walter Pitts, and the two start talking. And McCulloch is a researcher, he's a neuroscientist. And again, the two seem really different. We've got this neuroscientist on the one hand, and we've got this very formal logician. McCulloch sees that Pitts is really struggling in terms of his life, and he invites him to come and live with him and his wife. In fact, Letvin and Pitts both go to live with McCulloch and his wife. And Pitts and McCulloch in the evenings talk about their ideas about science. McCulloch talked about neuroscience and the brain. Pitts talks about logic. And over time, they start to ferment these ideas about how actually what's happening in the brain with the neurons could maybe be seen as some sort of formal mathematical system. And they end up writing this paper together, a logical calculus of the ideas immanent in nervous activity. And essentially this is saying, hang on a minute, if we look at the brain and what the neurons are doing, maybe we can think of this as doing logic. Maybe actually everything that you can do in logic, you can do in the brain, and everything you can do in the brain, you can do in formal logic. And there's this sort of synergy between the two. They actually write another paper. Oh, shall I try and hide this? They write another paper together a little while later. You might not be able to see that at the back. It's called What the Frog's Eye Tells the Frog's Brain, which actually says, okay, these ideas that we came up with before, they're a little bit simplified. But this was really the first paper to say, hang on a minute, maybe there is some relationship between what happens in the brain and computation, logic and computation. In fact, they published this paper, and neither the neuroscience community nor the formal logic community found it very interesting. It was sort of ignored at the time, but really was the first piece of the puzzle that said, maybe we can take ideas from neuroscience and think about them in terms of computation. So we go forward quite a bit further to Frank Rosenblatt, who was working with the US Navy. And he came up with an idea which essentially said, okay, if you can think of a single neuron as this sort of thing that does logic, that sends a binary signal, a 1 or a 0, can we put them together in any way into a form which itself is going to do a computation which is more interesting than just a yes or no, a single binary response? And so what he does here is he comes up with the idea of a perceptron. And a perceptron is really the sort of underlying unit of a neural network. Indeed, even the neural networks that we have now, the basic unit in some sense is a perceptron. And the idea of this, we see this sort of cartoon here. If you've got an image, and you can think of these as pixels these days, but if you have an image and you have an X drawn on the image, maybe you have a load of images. Some of them have X's drawn on them, some of them has Y, some of them have other letters. And you want to have some computational system which is going to look at this and tell you, yes, there's an X on here, or yes, there's a Y on here. So the idea here, you take this image and you split it up into the equivalent of pixels, and each of those pixel values goes through some computational system where essentially each one of the values goes into a single unit here and then is summed in some way such that you're then going to get an output signal. We're going to go into this in more detail, but essentially what you see here is that all of the red region here, which is where the X is, goes to these little units here, and they get summed together. And if you've got signal coming from them, so let's say this is drawn in red on a black background, and if you've got some signal coming from those, it's going to sum together. And if enough of them sum together such that you have the requisite shape to form the X, it's going to output a signal which is a 1 for X, and everything else is going to be 0. Okay. We'll go through some more details of this in a bit, but this is the basic idea of the perceptron. In fact, this is what the perceptron looked like, a fairly complicated piece of equipment, but essentially all it did, it took a picture, passed the picture through some logical set of gates where each of those logical gates was equivalent to a neuron. It's got inputs coming in, it fires a signal out, and in this case it's a sort of continuous electrical signal, but it fires a signal out, and you have a number of outputs, and depending on which one of the outputs fires, you go, okay, this was an X or a Y or a Z. Okay. The key here is, how does the wiring in the middle work? Okay. What's the configuration that you need such that when there's an X in the image, it outputs a 1 for X and 0 for everything else? And the answer there is that, well, you need to change the configuration of these and indeed change the weights, where the weights are equivalent to the synaptic connections in the brain. So remember, you've got one neuron connecting to another neuron, and the importance of this signal coming in is encoded in the synaptic strength. Essentially, it says, I've got a 1 or a 0 coming out here. What do I multiply that by coming into the next one? Okay. And you've got an equivalent here where you've got a set of weights, which are really like the electrical connections, and you get to tune these. And of course, if you set this up randomly and you put an X in there, then it's going to output something which is nothing to do with the X. It's going to give probably, just some random signal coming out. And then you want to tune the weights. You want to change the weights a little bit so that when you show it an X, it outputs an X. Okay? And of course, not all X's look the same. You know, some are going to be slightly different angles. And so over time, what you want to do is that whenever it sees something like an X, it outputs 1 for X and 0 for everything else. Such that if you show it an X that it's never seen before, but is in some way similar to other X's, it outputs a 1, not a 0. Okay. So at the time, the New York Times said this is the embryo of an electronic computer that the Navy expects will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. This was maybe a little optimistic, but maybe, you know, where are we? About 60 years later. Maybe we're coming to the frontier where actually this is the case. I'm not going to talk about the consciousness of machines, at least in this talk, but you know, it's something that people are beginning to take a lot more seriously than they were just a few years ago. Okay, so let's just think about this quickly in terms of images and pixels that we think about today. So this is a data set called the MNIST dataset, and essentially it's a data set full of pictures of handwritten digits. You see here loads of 1s and 2s, and the 2s will look a little bit different, but they're mostly clearly 2s, and the 7s are mostly clearly 7s, but you know, maybe that one looks a little bit like a 1. And this is something to think about, that actually, you know, although we've said that those are 1s and those are all 7s, there's some ambiguity here. So even if you were to give this to a person, they wouldn't all necessarily give you the same response. They wouldn't say necessarily, yeah, that's a 7. Somebody would say it's a 1. So the idea of a computer being able to give you 100% accuracy on this doesn't really make sense, because in a sense there is necessarily ambiguity in a data set like this. Okay, so you take a 5 and you look at it at the pixel level, and these pixels have values where this will be a pixel value 0, and this will be a pixel value 250. Generally, there's a range. It can take values over 255, and essentially it's the pixel intensity. Okay? And you want to take those signals, the pixel intensity, pass it into something equivalent to a perceptron, and you want it to output in the 5 output. You want it to output a 1, which says yes, this is a 5, and everything else it gives 0. Okay. So how does this actually work? So let's take a slightly different and simpler data set. So let's think of a classification task here, where maybe we want to think about the COVID outcome based on a series of features. And this word features is important in that this is the word which is used. You have a set of features here where a patient may have an age, a blood pressure, maybe comorbidity, the vaccination status, previous infections, etc. And there may be a binary outcome, a good outcome of them having COVID, or a bad outcome of them having COVID. Okay, and maybe we'll just take 2 of these features, just blood pressure and age, and I've made up this data completely. But here, the red I'm implying is a negative outcome, and the green is a positive outcome. Maybe this is they recover quickly or they don't recover quickly. And we can see here that if somebody has low blood pressure, hopefully this isn't 0, but if somebody has lower blood pressure and they are a lower age, within this data set that I've made up, looks like they're going to do better. Okay? And these ones over here look like they're going to do worse. So if I gave you this data set and I appropriately put numbers on here, and then I gave you some new patient and said, okay, this new patient, well, their age is this and their blood pressure is this, you would be able to make a guess that, well, probably because they're over here, they're probably not going to do very well. Okay. And so what we really want to think about is a decision boundary. Okay. Can I draw some line through here such that everything above the line I'm now going to predict is going to do badly, and everything below the line I'm going to predict is going to do well? So I give you this one here, and you'd see it's above the line, and so you go, okay, well, given the data, the data from past people, it looks like this person probably isn't going to do well. Okay. So we can think of this in actually a mathematical way. So let's take the age of a person and multiply it by some number W1, it's the weight. And the blood pressure, and let's multiply it by a number W2, weight, and let's add some bias, B. And we're just going to form an output here, which is some very simple combination of these 2 features, just B plus age times W1 plus blood pressure times W2. Okay. And then if the output of this is greater than 0, you predict 1. And if it's less than 0, you predict 0, where 1 might be a bad outcome and 0 might be a good outcome. Okay. So depending on the value of W1, W2, and B, essentially this is going to give you different decision boundaries. Okay? If I change W1 and W2 and B, it's going to shift this line, because really this output here, if it's above 0, it predicts 1. If it's below 0, it gives you 0. This gives us a decision boundary. Okay? And each one of the values of W1, W2, and B is going to give us a different decision boundary. So if I start off with some random value of B and W1 and W2, I've got some line here, and that's clearly not the right decision boundary. Okay? It's clear that if I try and split the data up here and down here, well, here you've got both good and bad outcomes, here you've got good and bad outcomes. You're not making the correct predictions. Okay? This one here, there seems to be a lower error. And this word error is, there's a technical meaning for it here, but essentially you can see that mostly it's correctly predicting that everything above the line is a bad outcome and below the line is a good outcome. Okay? Maybe it's got a couple that it's identifying incorrectly, but it's certainly a lot better than the completely random one. And then you've got the optimal line, the optimal decision boundary, which in this case actually has no error at all. So the question here is, how do you tune W1 and W2 and B such that you get this optimal error, the optimal decision boundary? So what you really want to do is define some error where the error is a function of how many of the people you are misidentifying. Okay? Where someone was a good outcome, you're predicting that they're a bad outcome, or vice versa. Okay? I'm simplifying things a little bit here, but that's the basic idea. And then we can plot here, and I'm just going to plot in 2 dimensions, W1 and W2, where what we can see here is that for some particular value of W1 and W2, which corresponds to this poor decision boundary, that's clearly not the right one, we've got a high error. And then this one here, which is certainly a better decision boundary, we've got a lower error. And then down here, this is the optimal one where we've got maybe no error at all. Okay? So what you really want to do is to tune the values of W1, W2, and B, if you've got the 3 parameters there, so that you move down this error surface so that you can find that point. Okay? And there are ways to do that using fairly simple mathematical tools. It's called gradient descent. And essentially the idea is you might not know all about the details of the structure of this surface, but I do know that at that point, I can move in some direction, which is the direction of steepest gradient. Okay? And I just move down a little bit here, and then I ask the question again, what direction do I need to move to go in the direction of steepest gradient? And if I keep doing that, I'm going to end up there. Okay? So this is sort of an automatic way of tuning these parameters such that I get the optimal decision boundary. Okay, now I've got my optimal decision boundary. Now I can take a new patient and pass it in and say, okay, is this person above or below the line? Make the prediction. So in that case, I was talking about essentially 2 weights and 1 bias term. The B is called the bias term. But you can think about having something where you have many, many features. So rather than just age and blood pressure, maybe the features are the pixel values of a 1 megabit image, okay, on the order of 1 million values. Okay, each one of them gets multiplied by a weight. There's some bias, and then you can apply some function to this, which outputs in the end a 0 or a 1. Okay, and we'll see that this allows us to do classifications of pretty complicated things. So this object here, this mathematical object, is the perceptron. And you can see here that it's got some resemblance to the real neuron, that you've got these inputs. Something is sort of somehow being integrated here, depending on the weights, and then there's some output, a 1 or a 0. So it turns out that this is very useful, but it's quite limited. And in this book by Minsky and Papert in 1969, they showed that this on its own had some very, very strong limitations. There were types of problems that you couldn't, or certain data sets where you couldn't correctly classify the data. Okay, I think, yeah. So in fact, if you just took the perceptron that we had before and you tried to classify something like this, where you've got maybe good outcomes and bad outcomes in the middle, there's clearly no straight line that can correctly separate one set of outcomes from another. But here you can see that, well, a circle does give you a decision boundary. Everything inside the circle, bad outcome, outside the circle, good outcome. So this book by Minsky and Papert, called The Perceptron, actually showed that there were major limitations to this very basic architecture. And in fact, it was really the sort of catalyst for one of the first AI winters, which essentially put the research in AI back a very, very long time, because people said, okay, we've got this idea of neural networks. Actually, it can't do the sorts of things that we really want it to do, because most data is not clean like this. There's not sort of a linear separation. Most data, you've got some very complicated separation boundary or some circle. It's generally much more complex. However, actually, you can take these perceptrons and you can put them together. So if we've got some perceptron here, the output of that can go into another perceptron and can go into another perceptron. This is called a multi-layer perceptron. And if you do that along with so-called nonlinear activation functions, you can actually classify much more complicated types of data. We good? Yeah, cool. So how might we think about this in terms of pictures? So here I've got a load of pictures of cats and a load of pictures of dogs. So a single picture of a cat here, we can think that it's made up of a load of pixel values, and each of the pixel values is a number. Okay? And so I can take that and I can sort of take the matrix, the array of those numbers, and I can concatenate them. So I can concatenate them so I've got this long string of numbers. Okay? And you can actually think of that. So let's say this is a 1 megapixel image. I can think that this image, given by these roughly million numbers, corresponds to a single point in a million-dimensional space. Okay? I'm not drawing the million-dimensional space. Here I'm drawing it as if it was just a 3-dimensional space, where this cat image is a single point here. Okay? The coordinates of that point, it's x, y, z. So the coordinates at this point might be 0.5, 0.5, 0.5, maybe to that one there. The 0.5, 0.5, 0.5, which are the coordinates of that point, correspond to the data in the image. Okay. Of course, this image is a million-dimensional, so rather than it being 0.5, 0.5, 0.5, it's going to be a million-dimensional coordinates. Okay. But each of these pictures just corresponds to some point in this space. Okay. Now we can see here, and again, I've made up this data, but we can see here that I could sort of put some slice, some surface in the middle of this that would separate on the right-hand side pictures of dogs and on the left-hand side pictures of cats. Okay? Of course, it's much more complicated than that in reality, but you can see the idea that a single picture corresponds to a single point in some high-dimensional space, and over here are cats, and over here are dogs. And I can put in some decision boundary in exactly the same way as we had for the previous case, but we're just in a higher dimensional space now. Okay. So what do? We take a picture of the dog and we pass it through. We've got all of these weights, and we're going to be moving these weights around, and it outputs cat. Okay, that's an error. So what we actually have to do now is something called back propagation by gradient descent. And what that really means is we take this and we say, okay, this is different from what we wanted. We pass the information back through the network and we tweak automatically the weights in each of the perceptrons such that next time you give it this picture, it's more likely to give you the output dog than it was before. Okay, we're training the neural network. Okay, I don't think I've used that word yet, actually. So neural network is, well, the multi-layer perceptron is a type of neural network, a network of neurons all concatenated together. This is what's called a deep neural network, where here we see we've got sort of an input layer here, where the data actually goes into that layer. We've got an output layer here. Each one of these is called a layer. And we've got a load of hidden layers, which aren't directly connected to the input or the output. So here we've got, what, 1, 2, 3, 4 hidden layers in the middle. And generally, when you've got multiple hidden layers, you call this a deep neural network. So you can do this for all different sorts of data. So actually, it turns out, and this is a little bit of a cartoon again here, because what we have essentially is a series of pictures of faces. And the idea is that you pass each one of these faces through, and maybe you want to do some classification of the faces, maybe into, happy or sad. Or in this case, maybe you've got 4 different outputs. Maybe you want it to be happy, angry, surprised, and sad. Okay, that's what you want to predict. So rather than just having 2 classes, now we've got 4 that we're trying to classify the pictures of that. Okay? And again, we pass each one of them through, and each one of them is labeled. This is really important. In the same way that previously you've got a load of pictures of cats and dogs, and these ones are labeled as cats, and these ones are labeled as dogs. You need that labeled data to train the network in the first place, so that then I can take a picture where it's not labeled. I don't know whether it's a cat or a dog. I pass it through, it gives me some output, and that's the prediction. Okay, this is now predicted to be a dog. In the same way, each of these faces is classified by hand as, happy or sad or surprised or angry. You train this so that it outputs the correct label. In doing so, you're changing the weights, and I can now take a new picture and pass it through, and it's going to give me some prediction. Okay, this is a picture which wasn't in the original data set, and it's predicted to be happy. So what's actually happening here is something which is very similar to what happens in the visual cortex of most animals' brains. Essentially, the very first layer is really picking up these very, very low-level features, edges, curves, contrast between black and white. The next one is putting them together into sort of slightly more abstract, high-level features. We see things which look a bit like ears and eyes and noses. And then the last one is putting them together into sort of stereotyped images of happy faces or sad faces. And as the image goes through, it's going to essentially activate different combinations of these, so that by the end, the happy face is going to activate the stereotyped happy neuron, okay, and is going to output happy. So we're going to take a really quick sort of journey through the history from the perceptron in 1958 all the way up to, well, the 2010s. There's a lot that's come since then, but to give the general idea. So we've got Frank Rosenblatt in 1958, and then 1969, Papert and Minsky come along and they write this book, Perceptron, and this puts a halt on a lot of the development on neural networks. People are working on other aspects of AI at the same time, not just on the neural network sort of picture of things. People are working on things like expert systems and language systems. And the idea of an expert system is it's a set of rules, and essentially you're hard coding in a set of rules on a computer such that if you go and ask it a question, maybe an example might be you're a doctor, you've got this expert system coded into your computer, and a patient comes in and they've got a load of symptoms, and you put in, my patient has symptom X and Y and Z, and the way the program has been encoded, it's a sort of logical set of statements. If this is the case, then if that's the case, then this is the thing that they're likely to have. If they have X symptom and they don't have Y symptom, then this is the prediction. That's the general idea of an expert system, and they can be extremely complicated. Essentially, an expert has sat down and written the set of rules that are needed to make some particular decision. The diagnosis of a patient. And this is importantly different from what's happened with the neural network, where the rules have been learned from the data. So for a neural network, the rules are encoded in the weights and biases in the neural network, and those are learned by automatically feeding the data in. You don't have to, with a neural network that classifies dogs from cats, there is nowhere that you have to code in, if you see whiskers, then probably cat. If you see wagging tail, then probably dog. That's different from an expert system where that's exactly how it works, or more or less how it works. That with an expert system, it's sort of a procedural, logical set of steps that are hard-coded in by an expert. And indeed, this is what happened with the first AI winter. So 1969, essentially people had stopped working so much on neural networks, but they were working very heavily on these ideas of expert systems and languages and machines. And in 1966, this was, and then 1972, two reports came out that essentially said, look, there are massive limitations with these systems. In fact, it was said in this report by Lighthill, in no part of the field have the discoveries made so far produced the major impact that was then promised. Essentially, people had thought that these sorts of very, very basic chatbots would be able to interact with people, in the way that we now have chatbots that we can interact with the likes of ChatGPT, and it just hadn't come to fruition. The the necessary complexity of putting in all of the rules just wasn't possible at the time. Okay? There was also this idea, so this is the so-called Chinese room, and the idea there was that you couldn't get a computer to really understand in the same way that if you put somebody in a room and fed through Chinese questions, the person in the room would be able to look up in a set of rules the corresponding answers and would be able to output the correct answer with some very large ledger book of rules. But of course, the person wouldn't understand. They wouldn't understand Chinese. At least that was the idea. In fact, people like Douglas Hofstadter have disagreed with this argument, because essentially it's true that if you have a very simple set of rules and a limited set of inputs, then you don't need a lot of complexity there. But if you want the complexity that you see the likes of ChatGPT outputting, maybe there is some understanding there. And this is a major debate that people are having about whether ChatGPT actually understands what it's doing. We can talk about that in the next talk. Okay. So far I've mostly been talking about sort of images using neural networks. But of course, things like ChatGPT don't work on, well, they do work on images now, but the first instantiation of them work purely on language. So how would you think about feeding language into one of these systems? A picture, well, there's clearly spatial information, which is important. It's important, the relationship between the positions of the pixels, but it's not sequential in the way that a sentence is. So here we've got a sentence, such a bad movie. The order of these words is really important. And so the question would be, how do we feed this into a neural network? Because here, the multi-layer perceptron that we wrote before, you feed in information in one go, and then there's an output. What you really need is some sort of memory. If I tell you a word, such a bad movie, by the time we got to the word movie, which came later, you remember that we've already said such a bad. Right? So you need to include some sort of memory in the system. And the way to do that is to include what's called a recurrent layer. And the recurrent layer essentially works by you feed in the first word into the input layer. It goes along and it's going to continue going through, but you're going to take the output and concatenate it, put it together with the next word. So you put in such, it goes through, it's transformed in some way by the weights and biases, and then is combined with A. Now we've got information about the such and A, and then bad, etc., and it goes through. And you might want to use this for something like sentiment analysis. Sentiment analysis essentially says, I've got a load of reviews of movies, and I want to classify them again as positive or negative. And so such a bad movie, we know that this is negative. But just because the word bad is in there is not enough information to us that this is a negative movie review, because of course it could say this is not such a bad movie, okay? Or many, many different combinations. So this idea of the recurrent neural network by Shinichi Amari came along in '72, and it was pretty good. It could do things that the sort of image-based systems couldn't do before. It could do translation in a very simple way. So how are you? Gets translated. There's a sort of stop symbol that says, I'm going to put in some information. How are you? I'm done. Okay. Now I want you to translate it into Italian. Okay. And there's some set of rules for taking the tokens here. I'll talk about tokens in the next talk in detail, but the words here and turning them into numbers and then turning numbers back into words. Okay. Again, it's all encoded essentially in the weights and biases of the neural network. So the idea that I spoke about before, where we take the incorrect outputs, so we put in a picture of a dog, it outputs that it's a cat, and we so-called backpropagate that information back through the network to tune automatically the numbers in the network. So this idea of backpropagation came about in 1986 by Hinton and others, Geoffrey Hinton, who's one of the most important people in the field. And this really changed what we were able to do with these systems, because before we didn't have efficient ways of training these multi-layer perceptrons. In 1989, This was by Schmidhuber, Jürgen Schmidhuber, who's done a great deal of very, very important work, came along with the idea of a convolutional neural network. And this is a particular architecture of network. I'll use that word a few times. So the architecture really means how the neurons are combined, how the individual pieces of the neural network are combined. And in a convolutional neural network, essentially you've got the equivalent of a sort of filter that runs over the image, some small filter that runs over the image and picks up spatial information and then combines it together. So this idea of a convolutional neural network was able to use the explicit spatial information within the network to usefully take information from the picture. Okay? Convolutional neural networks are generally the way we now do image classification using neural networks. So indeed, so the expert systems had essentially failed, and we had a second AI winter, and really a lot of that was to do with the fact that now we had these impressive algorithms, but what we didn't have was the computer power. Okay? That's really something that's changed a massive amount. We had convolutional neural networks and adaptive recurrent neural networks, but we couldn't do all that much with it because the computer power we had wasn't enough. We couldn't at this time, you know, in the late 90s, we simply couldn't do classifications of things like dogs and cats efficiently. You know, that's something which is sort of one of the first examples you might do when you're learning about neural networks now, is just take a picture of 100,000 cats and dogs and write in a few lines of code a neural network which can classify them. There was a problem with the recurrent neural networks that I spoke about before, and that problem was essentially the fact that with the way that it works, you've got this sort of memory module, and it remembers things recently that you've put in, but it's not very good at remembering stuff from a long time ago. It all gets sort of overwritten in a way. This new architecture, also by Jürgen Schmidhuber, the long short-term memory, essentially had a way to remember and forget. So you could take in information and it could say, actually, I don't think this information is very important. I'm going to forget that. Okay? And it turned out that this really, really helped with this problem of not having information from a long time ago in the sentence. So, you know, if I've got the sentence, such a bad movie, that's fine. You know, it doesn't, I don't have to remember a great deal. But if you've got a story or a paragraph, stuff that happens at the beginning may be very, very important to what happens at the end. And having that relationship, being able to remember what happens at the beginning, is clearly important. And LSTMs went a long way to solving that problem. This probably isn't very visible there. But so the pre-training of these so-called deep belief networks was really important in the early 2000s. It's a slightly different sort of architecture of neural networks. But by the 2010s, we were able to do image classification in pretty complex ways. So so-called ImageNet had, I don't remember, it's many millions of images. And essentially, you could not only, you know, give it a picture of a cat or a dog and say this is a cat or a dog. You could tell that something was a mammal, was a placental mammal, carnivore, canine dog, working dog, Siberian husky. You could go down to really, really deep levels and do sort of multi-category classification. You could tell something's a vehicle, a craft, a watercraft, sailing vessel, sailboat, trimaran. Okay, so it was able to do classification across very, very complex categories. So this paper, the ImageNet paper by Jia Deng and Li Fei was extremely important for putting together this database, which is still in use today. And by, where are we, 2023, these new types of networks were able to classify to sort of on the order of 90% accuracy on these sorts of images. And indeed, just think about this. This is able to tell the difference between a Siberian husky and another sort of husky, and a trimaran and other sorts of sailboats. This is something that most humans wouldn't be able to do. Right? The different sorts of categories that ImageNet is made up of is pretty complex and is beyond what most people could do to the 90% level. So this, by now, is beyond most human experts. I'm just going to go into this very, very quickly, and then I think I'm going to wrap up and see if there are some questions. So this is sort of general AI ontology, a general framing of where everything fits in, because I've really only been talking about supervised learning here. Supervised learning where I give you a data set and it's got labels. What happens if I give you some data set which doesn't have labels? So, for instance, maybe I give you some data set where we've got ages and blood pressures of different sorts of people, but I don't tell you anything about those people. And your job is to say, there seems to be a cluster over here. Certain types of people are clustering over here, age and blood pressure, and certain types of people are clustering over here, age and blood pressure. And the job of an unsupervised learning algorithm is essentially to be able to say, I see clusters here. I see some structure in the data, and to tell you what that structure of the data is. Okay. So there's supervised learning and unsupervised learning. You're given the labels, you're not given the labels. And you can do this either, with something like simple linear regression. This is just a straight line fit to a set of points. Or you can use a deep network to do something like image classification of galaxy types. And so each of these, you can apply deep learning to each of these. So you can have supervised learning in the classical sense, just straight linear regression. Or if I apply deep learning, then it's deep supervised learning. Okay. So all of the stuff in here is machine learning. And essentially that means give a machine data and it will learn the rules for itself, which to me, there are disagreements within this. You speak to people in the computer science department or stats department, and you will find slightly different perspectives on this. But to me, this is within the field of artificial intelligence, where things like expert systems and formal logic, knowledge representations fit within artificial intelligence, but are not machine learning because it's not the machine necessarily learning for itself from the data. And then there's reinforcement learning, which is the main area that I actually work in, which is really about how do you get machines to perform tasks for themselves through trial and error learning, in the same way that we learn through trial and error learning. I give you a new task to do, here's a game, learn to play the game. You'll try some things, you'll get some points, maybe you'll lose a life, whatever it is. You'll learn through trial and error how to play the game. And that's the basic idea of reinforcement learning. Okay. A massive amount has happened since then. Okay? So generative adversarial networks, these are pictures of people who do not exist. In fact, there's a website, thispersondoesnotexist.com, where each time you refresh the page, it'll give you a picture of a person that does not exist. And each of these people here, these are examples of people that are generated by what's called a generative adversarial network. I can talk about the details of that later. It's a really interesting sort of architecture. But essentially, you can generate these sorts of images in the same way that we can now generate text in the likes of ChatGPT. This is going to work. So I don't know if you've seen, who here has seen Sora? A few of you. So this video down here is a completely computer-generated video. Okay? This is not a real person walking. This was generated by somebody typing in, I would like, a picture of somebody walking through a Tokyo street at night in a particular style. In fact, this comes from OpenAI, and this idea of generative AI, although it seems to be very different from classifying cats and dogs, the fundamental architecture is they're essentially the same. It's still information coming in the form of pixels, or information going out in the form of pixels, in this case, and weights and biases. That's really all it is. The structure of the neural networks are different, and now we're using the so-called transformer or retention network, which I'll talk about a little bit next time. But really the fundamental idea of all of this is the same. You've got this neural network, it's full of weights and biases. You train it with data which changes the neuron, that changes the weights, in exactly the same way that your interaction with the world changes the synaptic connections in your brain. You learn about the structure of the world through interacting with it. That's what's happening with these. They're interacting with it in a fairly sort of controlled way. And they're learning then to reproduce in the same way that I've listened to lots of people talking, and that's changed the synapses in my brain. And that's now allowing me to figure out what the next word is in the sentence that I'm going to speak. Okay? I don't have some big picture of what it is. I'm just really doing next word prediction myself. Okay? And that's ChatGPT, and that's what I'll talk about in the next talk. I think it's probably about time to stop there. Yeah, let me know if there are any questions.
Thank you. Thank you. That was quite a ride. we can take some questions. I don't know if we can take off the slide so we can see people. So while you're thinking of any questions, there has come one in the chat, if I can read out. You can see it, but it's someone's asking, well, thank you for the excellent talk. A slightly random question, but when you log into an account, there's sometimes an image where you have to identify transport types.
Yes.
To or fire hydrant. Is that the purpose of helping AI development?
So that's a great question. So these captures the idea of having to say, okay, there's a fire hydrant or there's a bicycle here. It has actually been used in the past for assisting with the training of AI. In particular, I haven't seen them for a while, but the ones where you had to identify a word, a set of letters, that was actually used for automatic translation of text, where the OCR didn't work very well, and essentially it was augmented by people training up the system to be able to do better. So certainly in the past that has been used. The ones now where we're doing sort of fire hydrants and the like, to be honest, lots of AI systems could do those really, really easily now. Pointing out where within the image, is the fire hydrant. So the idea of the capture is probably not going to exist much longer, at least in the form that we have now, I would guess, because most AI systems can do that fairly simply.
So you could be a robot.
Indeed, yes.
Okay, we will take one question and one question. Go ahead.
It looks like everything is linear on the perceptrons and the multi-layer perceptrons. It looks like linear. Is that true?
So I missed out the idea of these non-linearities. And so if it's fully linear, if the output is just multiplying numbers together and adding things together, you're only going to be able to get what's called a linear decision boundary, and maybe a high dimensional decision boundary, but it's always going to be linear. If you want anything which is non-linear, then all you need to do, strangely, is add a little non-linearity in the output of the neuron, essentially the activation. So you take the output of a neuron, you apply some little non-linearity, which basically says the input is not directly proportional to the output. And doing that allows you to do these much more complicated things. So I didn't talk about the non-linearity there, but yes, all of the neural networks that we use now have these non-linearities.
In the back?
Thank you, John. I learned so much. Can you just briefly go back to the question of long short-term memory and the importance of forgetting?
Yeah.
And what that development was?
Yeah, sure. Yeah, so the question there was with the LSTM, the long short-term memory, what was the utility of the forgetting, or what's the importance of that? So the idea there is, let's say you're reading a book. You've got some sort of hidden state in your brain, which is sort of this current picture of what is happening in the book. And that's being updated all the time by each word that you read. But you might read a word, maybe the word the, and your brain can essentially say, I don't know if this is actually how the brain works, but you can imagine that your brain might say, I don't really care about the word the. It's not really important. Maybe there's some representation that I can take from it, but I don't need to remember that the word the is stored in my hidden state. So as the LSTM goes along, it chooses whether to keep or forget certain parts of the information that comes in. And that basically makes it much more efficient rather than trying to remember everything. If you were reading a book and you had to remember every word in order to remember anything, it's essentially going to be useless. Unless you've got some incredibly high dimensional space that you can store all this information in. You really want to be able to get rid of as much information as possible. In the same way that, as you're looking at a scene now, you're not taking in a conscious way all of the photons that are coming in. A lot of it is constructed, and a lot of it you're just throwing out. So because there is so much information in a lot of the types of data that we have, one of the most important things is knowing how to get rid of the stuff that doesn't really matter. And the LSTM architecture has built within it not just this recurrent loop, but has what's called a gating mechanism, which allows you to both forget and remember.
Okay, there's a couple of questions in the chat. Maybe we can take those too.
Sure.
So someone's asking, in the light of this timeline and the historiography of AI with the rapid changes, how do you imagine us capturing the history of development of the movement going forward?
Sure. That's a great question. So the question there was, what do we see going forward? We've got this sort of this relatively gradual trajectory in a sense from the 1950s with the perceptron until sort of the 2010s when things were beginning to ramp up, and then from 2017 it's just exploded. And I don't want to invoke too much the idea of Ray Kurzweil singularity, this idea that you sort of get to this point that technology is accelerating at a rate faster than we can keep up with, but it no longer seems as crazy as maybe it once did. That maybe we are reaching this inflection point that now it's not going to be the people are developing the AI systems. AI systems are going to be developing the AI system. And once that's the case, it's kind of, all bets are off. It's really hard. We don't know what happens when technology begets technology, which seems to be where we are now.
Cool. Okay. Deep breath. Okay, I will go for a last question from JP. So, given how much computer science is borrowed from neuroscience and psychology, do you know if AI tools have already been used to create more advanced medical or optometry treatment tools like contact lenses or eyeglasses?
So that particular example of contact lenses and eyeglasses, I'm not aware, but certainly the analysis of images of retinas and other parts of the eye certainly has been done. So to spot problems in medical imaging, absolutely AI is being used now. So a sort of simple example might be to look at an image and say whether there is some problematic set of cells in it. Very often they are now better than a radiologist at doing that. They can certainly do it faster. Thankfully, it's not being used on its own at the moment, so it still needs to be with the assistance of a radiologist. But yeah, absolutely, AI is being used certainly in optometry, in sort of neurosurgery, all of these areas. It's being used. Yeah.
Right. Okay, so we are on 2 o'clock. I do want to respect people's time, and also generally when we wrap up, we say, "Oh, shame, we haven't got more time." But actually, we've got another lecture that John's very kindly agreed to give next week. So hold your questions as well. Please add anything in the chat. So I'm just going to wrap up. Say thank you very much for today's lecture. I think just having this background just gives us a grounding in whatever roles that we have within the university, especially our sort of events are focused around supporting staff who teach. So I think that's really, really valuable, and I'm really looking forward to next week.
Good.
So thank you very much, and thank you to the online participants and for the questions. And hopefully we will see you next week as well.
Wonderful. Thank you very much. Yes.